Please welcome Louise Wright from the National Physical Laboratory.
Okay, thank you very much for the invitation to come and talk to you today. There's going to be a bit of a handbrake turn now. We're very much in more recent times. There are really three things I'd like to cover here. One is a bit of an overview of how we consider errors within measurement, because we don't always call them errors effectively. Another is to give you a few examples. So this is Rubens to Mars. And then the third one is really about how proper measurement science or metrology can help you to avoid common kinds of error, and in particular the ones that I'm going to be illustrating with the examples. That's not a coincidence. Okay, so metrologists in general are amongst the most pedantic scientists you will come across. If you have a conversation with a metrologist, then it will begin with, well, it depends what you mean by, and then a term that you had previously thought was simple. So in order to avoid constant bickering, we have something called the International Vocabulary of Metrology, or VIM, and I'll come to why it's VIM, not IVM, in a little while. But that defines measurement, as you can see there, as the process of experimentally obtaining one or more quality values that can reasonably be attributed to a quantity. And then we have to state what a quantity is. And it's essentially a physical property that you can define with a magnitude, a number, and a reference. And then if we look at error, it's defined within the VIM as the measured quantity value minus a reference quantity value. Now, the trouble is that for most of the measurements that we make, the reason we make them is so that we can get a value for them. So we don't have that reference value in most cases. So what we have to try and do instead is eliminate, reduce, correct for what we can, what we know about, and try and estimate or bound what we can't. So I'm going to talk a little bit later on about how we manage that process. But one of the steps prior to managing that process is to look at the typical causes and effects. And we can think about these in two ways. We can think about the sources of the error, and typically within measurements, you're probably hitting multiple ones of those five. In particular, people are a major problem, not just because they don't do things perfectly, but also because all communications are imperfect. What's in my head and what's in your head when we talk aren't the same thing, and that may mean that you don't do what I think you're going to do, no matter how explicit my vocabulary is. And then the other way that we can think about these is by the effect on the value that I am attempting to achieve and whether or not I know that error is there. So obviously I can only correct for or try to quantify errors that I know exist. This is back to Donald Rumsfeld and the unknown unknowns. This is really where the unidentified bit comes in. And those are often where we have the biggest problems, but they're also where we have the biggest opportunities for improvement, because they're the things that help us understand what we thought we understood already, really. The other thing I want to highlight is the point at the bottom, which is that increasingly we get errors in the overlap of multiple of these categories, in particular people and software, because again, the human-machine interface has been designed by somebody who thinks that you know what they know. So you can make fresh errors that they've never considered once you hand software on to other people, basically. So to move to the examples then, the first one I wanted to cover was the Mars Climate Orbiter. So this was a space probe that, as you can see, NASA launched in December 1998. And the intention was that this was going to go into orbit around Mars, as the name implies, and to be able to act as a communications relay for subsequent missions so that the signals could get back. But this, the contact was lost in September 1999, just as the satellite was entering orbit. And the interesting bit here is about how they calculated the trajectory for that orbit. So the software system that did this had two parts. There was a part from NASA that did the actual calculation of the orbit, and there was a part from Lockheed Martin that said how much you needed to push the engine to get the satellite to move a given amount, because Lockheed Martin had been responsible for the development of the thrusters. So what happened was clash of unit systems, essentially. The Lockheed Martin software provided the total impulsed firing in pound force seconds, and the NASA software expected the value to be supplied in Newton seconds. Now, the really interesting bit about this, to my mind at any rate, is that it was actually stated in the software specification document that Lockheed Martin were to do this, that they were to supply the source in Newton seconds, but nobody at NASA checked it properly. So that's not a Lockheed Martin problem, that's a NASA not doing the quality assurance correctly, in my opinion, and it seems to have been their opinion as well, because they didn't try and sue or anything. So what happened was, because these two sets of numbers are a factor of 4.5 different, you got a much lower trajectory than was expected, and what they think happened was either that it never entered orbit properly, went off into space, or it essentially burnt up because it was at a much lower orbit than expected, so it didn't have the appropriate heat shielding in place. So from Mars to Rubens, the Rubens one, the picture you can see here, and this was taken by a colleague of mine, we have Picture of the Month at MPL, and this won it fairly recently. What you can see here is the inside of Banqueting House in Whitehall, and it has some fancy paintings, and these were commissioned from Rubens by Charles I in 1629. But when they turned up, they were too big to fit in those spaces, so there was some fairly radical work going on with scissors in the background when they arrived. And the reason for this was that both Belgium and England and Scotland at the time used the foot, but their feet weren't the same. So what you can see on the right-hand side there is a conversion table from a German textbook from 1848. It's not terribly clear to read, but what you've got is a whole list of places like Baden and Vienna, and what else have we got? England and Denmark are in there, and each of them has a slightly different definition of the foot, so you've got a whole bunch of conversion factors there. But then on the right-hand side, you've got the metre, and a metre is a metre everywhere, as I will discuss shortly. So what can we learn from these two? The first is that units really do matter. You can't just give a number and assume that the other person is using the same units as you are. If we're going to exchange numerical measurement data, it has got to have a unit associated with that value, but also, if we're going to use units, then we've got to have agreed standards for the realisation of those units, because my feet and your feet aren't the same. So this kind of brings me to what is a unit? Well, I'm going back to the International Vocabulary of Metrology again, and it states that a measurement unit is a real scalar quantity defined and adopted by convention with which any other quantity of the same kind can be compared. So what sits at the heart of this is a comparison, and it's also useful that we can express the ratio of two quantities as a number. Now, this is something we have to be very careful with in some cases, because in order to express a ratio, you have to have a common value of 0, and that's not always the case for some things. If we use the ratio, it means we can meaningfully say this is twice as heavy or long or hot as that is. But in particular, for temperature, we all understand that 40 degrees C is not twice as hot as 20 degrees C, because the 0, it's possible to have negative Celsius values, basically. So it only really works as a measurement unit when to be consistent with that definition if we're looking at temperature differences. And similarly with time, if you think about the problems that occurred when railways entered Britain, and it turned out that different bits of Britain were using noon as the point at which the sun was overhead, well, that's not the same in different places. So that means that if I'm trying to run a timetable relative to a common 0, I have to define what my common 0 is, and that's when Greenwich Mean Time really started to be hugely useful. Now, this isn't a new idea. People have always known that this was a problem. It's acknowledged in the Magna Carta, as it says there. And this quote really, to me, illustrates the importance of consistency of measurement to trade. It's not just for science, it's for practical purposes as well. The other thing that's interesting here is that it says about the cloth, two L's within the borders. That says that we're not just saying this is a measure of cloth. We're being very precise about where that's being measured, because you can imagine that the merchant might be saying, oh no, I'm taking the borders into account, but no, this is defining carefully what needs to be measured. And again, this is an example of metrological pedantry. What you typically saw with the practical standards was that they were based on body parts or natural objects of a fairly uniform size or weight. So for instance, carob seeds were thought to have a consistent mass, and that's where we get the unit the carat from. It's derived from carob seeds. Turns out that they're no more uniform than any other form of seed of the same size, but people have ideas, as we've already heard. But as our knowledge and skills evolved, we started to move towards manufactured objects, because we could make those consistent, we could be confident that they were stable, and eventually we have moved beyond that, as I'll talk about next. So, the SI unit system then, this is really how global measurement data is exchanged these days. It started with the metre and the kilogram in post-revolutionary France, and they made actual physical standards for these. And then in 1875, we had the metre convention, where 17 nations, not including Britain, we were a little bit later than that, signed up to agree to use those measurement units, and each of them got a metre and a kilogram, so that they could be confident that a metre in Argentina, for instance, who did sign up in 1875, is the same as a metre in France. And that eases trade, but also it eases global science. It makes it possible to communicate with scientists in other places and be certain that their measurements and your measurements can be compared in a meaningful fashion. Now, this system gradually grew over the years, and we're now at 7 base units and 22 derived units. And since, there's also the multiplier powers of 10. So this is how we get to things like millimeters or terabytes, well, not terabytes maybe, gigahertz, let's say. These are really enable us to use an efficient shorthand for very large and very small numbers. The wheel you can see on the right-hand side has the 7 base units, and it also, in the inner wheel, has the physical constants that those are now defined in terms of. So we shifted in 2019. The last thing that used to be a physical standard is the kilogram. This was for years kept in a locked vault in Sèvres in Paris. And every so often, each institute around the world that had a kilogram would have to take it back and get it compared to the original one to check that your standard was still stable. But in 2019, we shifted so that these are defined in terms of the fundamental constants of the universe instead, and we're realizing them through experiments. Now, that's useful for 2 reasons. Reason number 1 is that physical objects are inherently fragile. So if anybody had ever dropped the kilogram on the floor at BIPM and it had split into 2, the mass of every single object in the world would have instantly doubled, technically, which is unfortunate. So you can see why we needed to move away from that. But also it means that as science evolves and we get better at measuring things, then our system will evolve to meet that without us having to redefine all of the units or anything. So what we have now, and I'm not going to read all of this lot out, but the SI is the consistent system of units in which each of those constants has each of those values, and we believe that that's going to take us into the future. Now, I mentioned earlier that metrology and consistent units are very important for trade, and what underpins that is their enshrinement as a legal system of units. And there are 3 countries in the world that don't use the SI at the moment. Those are Myanmar, Liberia, and the USA. So what we have is this kind of thing, where the vast majority of the world has it fully enshrined that metric is their legal system. You can see that the UK and Canada are both in purple. That's because we have a mixed metric and imperial system. So the vast majority of things that you buy will be labelled in kilograms or metres or kilowatt hours or whatever else. But there are some things such as draft beer, draft cider and milk that comes in returnable bottles that you are allowed to sell in imperial units. But mostly these days we're on the metric. So I work for the National Physical Laboratory and there are equivalents to us all around the world. Most of those countries that were in blue and some of the other ones have a national metrology institute, and it's our responsibility to develop and maintain the national primary measurement standards, so that's these experiments, but also to be able to disseminate them so that we can get the kilogram from the laboratory out to the scales in Tesco's, and I'll talk about how we do that in a minute. What you can see there is our main site in Teddington, but we also have increasingly laboratories in other places for specific types of measurements. So, in general, metrology enables you to avoid measurement errors by bringing trust in measurement data. I mentioned earlier that we're pedants, so we start off from defining what we're measuring and the unit and the scale, and then we agree how to put the definition into practice. So this is the mise en pratique. I didn't mention that most of metrology has a French underpinning, so a lot of it's VIM rather than IVM because it's in French. So a lot of the abbreviations we use end up being in the wrong order, but anyway. We also have that arrangement to ensure that measurements in different countries are recognised as comparable. This is called the mutual recognition arrangement, and means that we can trade internationally, we can do science internationally and so on. We use comparisons to link our measurements to the definition of the units. So this is what we talk about when we talk about traceability. So at the top we have a definition, and I've gone for the kilogram largely because it's easier to try and draw something that looks like a weight than it is to draw something that looks like an ampere. So we have a definition and we have an experiment that realises that definition, and then what we usually do is we take a transfer standard, so that's the kilogram, and we weigh it. We have a precise value for the weight of that object, and then we can use that to say how well our scales at the NMI are performing. We then do inter-comparisons with other NMIs to make sure that we're all measuring the same things in the same way, using transfer standards again, and then we're able to calibrate the equipment of other people and the transfer standards of other people so that we can make sure that a kilogram stays a kilogram all the way down this chain. So an industrial company can be confident that they are measuring what they think they are measuring. Now, there are things that change down this scale, and this brings me on to what uncertainty is, but I'm going to give you another example before I talk about that. So, my other example is around faster than light neutrinos. This came out of a project that was a collaboration between CERN in Switzerland and a laboratory in Italy, and the point here was that the neutrinos were created at CERN and received at the laboratory in Italy, and we knew what the timings were and we knew where both of those two laboratories were, so we could calculate the velocity of these. The preliminary results suggested that they were moving faster than the speed of light. Now, this is great in a way because science needs to challenge its assumptions. This is a challenge to scientific assumptions. That's a good thing. The only trouble was that there was an awful lot of evidence from previous measurements that suggested that this wasn't right. When they published the original paper, they stated that there was a 0.2 in a million chance of the result being a false positive, assuming the errors were entirely due to random effects, and I want you to remember that phrase. So, the way the velocity measurement worked was that you have neutrino production and neutrino reception, and those are taking place underground, and then on the surface we've got a couple of satellites to handle the timing aspect. So we have a couple of receivers, and those can see the same sets of satellites, which means they can get time signals from them, and they can be sure that the timing signals have a common zero. So we come back to, because this is a time difference we're trying to measure across two places, we have to know when zero is for this. And they're all sending their signals across. But the thing is that we have to get, and also each one had an atomic clock, so this is effectively a definition of the second that enabled them to check that the ticking was right on their time signal, so a second was definitely a second. But the difficulty is that you have to get the signal down to where the neutrinos are being produced and received. You can't just leave the time signal at the top, because your release of these things and your reception of these things is taking place underground, and you have to know when that happened. So the problem here was the known time and place aspect. The place was determined extremely accurately using geodesy and GPS as well. So there are some extremely interesting and mathematically complex ways of figuring out where you are, basically. I mentioned that they use common view GPS for the timing at the surface, and they check the second. But then you need to be able to correct the journey time for how long it takes your signal to get from the surface down to your neutrino things. So the problem here is that the errors were not due to random effects. In particular, there was a significant fault within the cabling system. Basically, something wasn't plugged in properly. So it's easily done. I mean, these are not simple systems. But still, so it meant that the neutrinos were being registered as having arrived much earlier than they actually did. And the final outcome was that they withdrew the result. We were able to keep with our nothing moves faster than the speed of light assumptions. And the statement was that the difference was approximately 6.5 plus or minus 15 nanoseconds. Now, that's a tiny amount of time, and you can see how important getting all of your corrections tied up and considering that complex system completely is. But there's a couple of interesting points from a metrological point of view. The first is that this speed measurement is indirect, and most of the measurements that we make these days are indirect. We didn't measure speed directly, we measured distance, we measured time, we used a mathematical model to bring them together, and increasingly that is the way that our measurements are working. The second is that the confidence in that result is effectively expressed as a hypothesis test. So it's expressed as the probability of there being a false positive. And the final result is quoted as being 6.5 plus or minus 15 nanoseconds. These are indications that measurement results within metrology are expressed as statistical distributions rather than numbers. And this is when I come to how we manage that process of our errors that we can't correct for. And this is what we call uncertainty. So the OED says that it's the state of not being definitely known or perfectly clear. The VIM says that it is a non-negative, at the moment, says it is a non-negative parameter characterising the dispersion of the quantity values being attributed to a measurand, that's the thing that's being measured, based on the information used. Now, what this reflects is the fact that if I had, for instance, a tape measure and attempted to measure the length of this bench and I did it 10 times, I probably get 10 different results. Repeatability is key to understanding measurement in many ways, because there are random effects that we have to characterise statistically, so that's automatically meaning that we're having to deal with probability distributions. There are systematic effects. Now, when those are errors and we can characterise them, we correct for them. But if we can't characterise them, or if it's going to be too expensive to characterise them, then what we try to do is bound them and typically describe them as a probability distribution again. So we're bringing these things together. And then we've got the problem around definitional uncertainty as well. But as I said earlier, this is why metrologists are pedants. So in general, no statement of a measured value is complete without an associated uncertainty for the vast majority of proper metrologists. So this means that we're dealing in this statistical approach all the time, but it's actually useful. Uncertainty sounds like a bad thing. It sounds like, oh, we don't know that. It's actually an admission that nobody knows anything, but at least we've put a quantified estimate on it. So what it really means is that we can compare data on a statistical basis. If we look at that top graph, then I know I've got two values and I know they're not the same, but I can't tell whether that difference is actually significant or not. Whereas if I'm able to associate uncertainties with the values that I've got, then I can make a more meaningful comparison, and I can start to understand, for instance, whether they're actually being driven by the same underlying distribution. If I haven't got that uncertainty information, it doesn't mean it doesn't exist. It just means I don't know what it is. So that means I'm being uncertain about being uncertain, and that's even worse. So I mentioned traceability earlier, and the uncertainty goes all the way through this chain, but it gets bigger and bigger as you go down, partly because you're getting further from the definition of the unit, and partly because NMIs have spent a long time and a lot of money trying to make sure that we can measure extremely accurately, but the industrial company might only need plus or minus 0.1%, so there's no point offering them something higher than that. Now, it's interesting because it means that calibration laboratories need to be able to evaluate the uncertainty as well. They can't just do the measurements, but also that industrial companies need to understand how to use this information, because what it enables you to do is make better informed decisions. And it's not just industry, it's important for healthcare and environmental science. Increasingly, these areas are underpinned by measurement, and if you have the uncertainty, then you can be more confident that your decision is appropriate, or you can manage the risks associated with you being wrong rather better. So because of this, we have a guide to the expression of uncertainty in measurement. This is kind of a de facto standard within metrology about how you go about calculating this stuff. It's available for free download, as is the VIM, if any of this is of interest to anybody. So just to summarise it very briefly, first of all, it requires you to have a measurement model that links the quantity that you're measuring to a set of input quantities. And then you need to assign the uncertainty information to the input quantities. And there's lots of guidance in there about how you go about assigning that information. You propagate the input uncertainties through your model to get you to a set of a complete distribution, and then you can calculate summary statistics as the result of the propagation. So that plus or minus 15 nanoseconds that we saw earlier, that will be a confidence interval, probably a 95% confidence interval for what the actual value of the time difference was there. And that will have been a summary of a much more complicated distribution, but probably probably approximated by a Gaussian somewhere along the line. So I want to finish up by talking a little bit about where metrology is going in the future. So the current system works for data from known sources, and historically that's what we've been dealing with. We've made measurements ourselves, or we've read about them in peer-reviewed papers. We can trust them. We know the provenance of the data. But increasingly, scientific data gets shared online, and we don't know who it's come from. So what we need are a set of tools that will still enable us to know about the traceability and the provenance and the units associated with the data, for digital data. So what we're setting up at the moment internationally as a global agreement is something called the SI Digital Framework. It's a set of machine-readable permanent digital identifiers with a semantic model that brings the kind of meaning to the links underneath them, so that we'll be able to associate unit definitions directly with our data when we share it online. AI is everywhere. I'm sure you're fairly bored about hearing it. But one of the things that we are trying to bring to the discussion around AI, and particularly the kind of AI that gets used in hospitals for decision making and things like that, is being able to associate an uncertainty with the output of an AI model. How do you go about that? The situation's much more complex than the mathematical models that we're used to. But we're already seeing AI used successfully within science at MPL. So what we want to do is make sure that we can definitely trust what's coming out of it, and really think about how we can help other people to demonstrate that errors aren't being introduced in what they're doing. And then finally, we're interested in new measurands, so new things that we can potentially measure. Most of what I've talked about so far is founded in physics, most of metrology is, but increasingly we are seeing an understanding that a lot of what happens in life sciences, health and biology is actually measurement. So for instance, MRI is getting to be more quantitative. But this leads to a whole set of new challenges, because if there's one thing that's really random, then it's human beings and their physiology. How do we capture that with an uncertainty? How can we develop standardized protocols that aren't going to be biased against one group of people or another? There are lots of interesting things around the kind of multi-scale nature of human beings as well, and in lots of other areas, including climate science. So I wanted to leave you with a few closing thoughts. The first is that we'd almost certainly have more errors if in 1875 we hadn't had the meter convention, because we wouldn't have a globally agreed unit system. Metrology is really there to put those units in place and providing a path to show that they are being consistently realised and disseminated. So this is the traceability, the intercomparisons. We can have confidence that we're doing things right. Uncertainty is really how we estimate the effects of errors in measurements, or at least the ones that we know about. And this is a good thing, not a bad thing, because it gives us richer information about what we've measured. Finally, as science is evolving and changing, metrology is keeping up to make sure that fresh measurement errors can be quantified and hopefully minimised, so that we don't end up with this kind of thing. Thank you for your attention.
So, time for some questions.
Your examples quoted uncertainty in the form plus or minus A. Can you have plus A minus B?
Absolutely, yes. So there are, if you consider the modulus of a complex quantity, that can only ever be positive. So, and if it's very concentrations similarly have to lie percentage compositions have to lie between 0 and 1, so you get asymmetric uncertainty intervals then, yes, absolutely.
Your 6 point something nanoseconds plus or minus 16 would come into that, in that the negative bits are unphysical.
That's the, hang on, talk amongst yourselves. Yes, no, one before actually. So this is a comparison though. So this is compared to the speed of light. So it's speed of light plus or minus. So it is possible to have that. Or, yeah.
It doesn't say that it could have come.
No, it doesn't say it went, no. Causality still applies, fortunately, yes.
Okay, the chap in white in the middle.
That's a great talk.
Thank you.
Yeah, that's great talk. We no longer have to worry about the standard meter changing or the standard kilogram being dropped, but we define everything in terms of the speed of light is this, and it's a number and it never changes. Mm-hmm. Have we swapped comparison, bringing physical things together, for comparability of experiment in multiple locations? And if that's the case, how do we ensure that those experiments are really doing the same thing other than bringing them together?
That's a really interesting question, and it's one we're attempting to answer at the moment. So whilst I said the kilogram has been redefined, the discussions are ongoing because the experiments to realise it are still being improved. There is, so again, we do send round, at the moment there is still this exchange of transfer standards and cross-checking, but there's also peer review of those experiments. So the people, there are two ways of realising the kilogram that are popular at the moment. One is the Kibble balance, and the other is a silicon sphere based on Avogadro's number and counting atoms. And the discussion around how to make those better is very much ongoing at the moment. So there's a group of experts that are, I don't know, because they're in competition with one another, there's a lot of, well, my number's right going on at the moment, I think, but we're gradually heading towards consensus and associated uncertainties. But interestingly, there are things around realisation of units at the point of need that are possibilities in the future, where it may be that what NMIs provide is a monitoring service and a cross-checking service to provide exactly what you've proposed, yes.
Okay, chap in blue here.
Thank you. Fascinating talk. The question you said you were standardizing the digital data as well. Would that mean that in the Mars orbiter, then the machine would know one's in Newton and the other one is in pounds, or if the digital input was standardized,
Yes.
it would recognize that those two don't work together?
Yes, absolutely. It would, assuming that both of those pieces of software had linked back to the relevant definition, then yes, it would enable the computer to understand that a multiplicative factor to correct needs to occur. So I mentioned that most of the world uses the SI as its legal metrology system. Within that, most of the imperial units are defined as multiples of the kilogram or the metre or whatever else. So it's kind of, they're not separate. They don't stand alone almost.
Chap in dark green at the back.
Thank you for a fascinating talk. No wonder I can't measure my curtains properly. I was really interested in the healthcare thing because how do we measure pain? Because my pain in the morning is different from my pain in the afternoon. And I've been having discussions, and it's about how do you feel today about your pain? And it's about a language. So if we're using AI to use a language model, what language does that model use that I can understand and the clinician or the professional understand to try and correlate that my pain in the morning is different from my pain in the afternoon? Thank you.
So I think there's two bits to that, possibly more, well, quite a lot of bits to that. One of them is that I would question whether your pain in the morning and your pain in the afternoon were actually the same quantity, because they may come from different sources. So a headache and a footache aren't the same thing. So maybe you've got multiple measurands. The other thing is around how I would call it quantification rather than measurement strictly, because whilst you're giving it a number, I cannot imagine how you can have a standard for pain effectively, unless we're going to kind of go around poking things into people's hands and saying, would you call that a 3 or a 4? It's an interesting one when it comes to perception, because we have looked at that before. What we've done in the past for things like texture is looking at whether we can map it onto something that we can measure physically. So perhaps we can measure brain activity in a particular area and correlate that with pain levels or something like that. I mentioned on the slide close to this one that a lot of things are indirect measurements. Even more things are actually proxy measurements, because if you think about when you're ill, you have your temperature measured. It's not that I'm actually interested in what the temperature of your body is it different from normal? And that's all I'm really looking at. And I think the pain thing's kind of related to that in some ways.
Chap here in light coloured jacket.
What's happened now is that there used to be a physical meter, didn't there, and a physical kilogram.
Yes.
All safely stored. And these have now been, the place of those have now been taken by transfer standards, presumably, that are then themselves checked against the speed of light and the equation you had for kilograms. How do you actually do that creation of the transfer standard now?
So the transfer standard does not have to be exactly a metre. It has to be a bar of fixed length that isn't going to change, that we can measure very accurately. So as long as what we've got is stable, isn't going to change over time, isn't going to bend, isn't going to expand as the temperature changes and things like that, it doesn't actually matter what length it is, because we can use the definition of the metre to define the length of it with an uncertainty extremely precisely. So we still use the same approach in as much as we have standards that are made out of materials that we know will not be affected by the various different things that we're concerned about, that we know the value of, and then we can use those as transfer standards, as you say.
Okay, I think we've got time for one more question.
Yes, going back to real basics of speed of light, the fundamental units you're using, so everything's converted. I couldn't write it down, but I noted the kilograms measured in, it's got Planck's constant somewhere. It's certainly got the speed of light. Very interesting, the speed of light. I believe the ancients said nature abhors a vacuum. Does a real vacuum, and the speed of light depends in vacuo, ideally, you can think about Platonic ideal. Can you actually measure it? Because is there such a thing as a true vacuum? Even out in space, there are things going on, gravitational fields, I don't know, I'm not a physicist. But the other thing is, I read somewhere recently that the gravitational constant can only be measured to about 4 decimal points, and to actually measure it, it's beyond that is not physically possible at this juncture. Could you comment on that? Will we ever reach an absolute true speed of light in a vacuum, and the very accurate gravitational constant? Is that possible, or is that something impossible?
Right, the second one I'm afraid I don't know enough about. So there's 2 constants that you could be referring to. There's gravity on Earth, which I'm assuming you don't mean 9.8.
I use that myself in engineering.
You mean the Newton one, the big G, not little g.
Yeah, big G. Absolutely. Yeah.
I don't know enough about that to be able to answer it. It's not something that we do.
Really?
But I am aware that it's not something that MPL does, no.
Oh,
it's
really?
yeah. Anyway, can't answer that one. In answer to your other one, yeah, you're absolutely right. There's no such thing as a real vacuum. But what we would do, what would we do? I don't know what we do. I'll find out and I'll get back to you. But I'm sure we do something.
Question for your organisation. Yeah. I don't know.
I'm not talking to the right people, clearly.
Okay. Well,
Okay,
thanks
right.
for your honesty.
Bring it to a close there. Thank you very much indeed. Can we give Louise a round of applause?